continuing from where we left off, or just to recapitulate what we discussed last time. Properties of the Fourier transform and delta delta functions. So these were the two things that we discussed last time. One, properties of the Fourier transform, two, the delta functions, and using these, we'll now try to find the Fourier transform of signals. So, do you guys already know how to find the Fourier transform of periodic signals? Anyone who has an idea, you can raise your hand. Okay. So, just cross checking, I'm audible, right?
Yes, sir.
Yeah. So, okay, because generally people know this trick of finding the Fourier transform of periodic signals, but okay, no problem. So, let us say that we have a periodic signal given by Pt that has a period capital T, right? We have a periodic signal Pt that has a period T, which means, or let's say T naught, which means that we can express sorry, this Pt summation right? This is the Fourier series, and right, this is coming the integral, yeah, right? So far we are good. Now, our discussion on that. Agreed? No, just a second. Coming. So, agreed with this? Or any problems with this? Oh, still delayed. So, you agree with this? I believe you do. So, therefore, yeah. So, therefore, guys, am I audible? Guys?
Yes, sir.
Yeah, okay. Because I shouldn't have used. I'll wait a second. I'll switch to the wired headset. Yeah, this thing has too many distracting sounds. The wired headset is way more comfortable. So I hope I'm still audible, right? Just yes would do. Anyone?
Yes, sir.
Yes, sir.
Select. Yes. So yeah, therefore Fourier transform of PT can be written as the Fourier transform of summation of k goes from minus infinity to infinity pk k 2 pi k by t naught t. Right now, Fourier transform has this linearity property, right? And summation is a linear operation. Also, these pk's, these are constants for a given k. Therefore, invoking k per t of Fourier transform well, summation k goes from minus infinity to infinity pk Fourier transform of k 2 by k t by t naught equal summation k goes from minus infinity pk delta f minus 2. So yeah, 2 pi shouldn't be there. Delta k by. Fine. No, sorry, this should 2 pi shouldn't be there. Earlier as well. My bad. Fine. Any problems with this? So this means that if I draw the spectrum, this will be P0, P1, P2, and these will be spaced. This will be 1 by T naught, this will be 2 by T naught, minus 1 by T naught, minus 2 by T naught,
Fine. So, and as you will realize that as this time period T naught, this increases, these grow closer. So, closer with increasing T naught, these grow further with decreasing T naught, or you can say increasing frequency. And as T naught tends to infinity, or as the signal tends from aperiodic to periodic, these will form a continuous signal in the frequency domain, which is the true Fourier transform. So we are running around in circles that way. Great. So that said, we are done with the basics. So now let us ask you a question. What? How do you define a time limited signal? Yeah. Question. How do you define a time limited signal? Guys, question for the class. How do you define a time limited signal? Come on. So I'll just randomly ask someone. Swaraj, how do we define a time limited signal? Yeah, Swaraj, unmute you. Yeah. How do we define a time limited signal? The question is for you, Swaraj.
Sir, I don't know, sir.
Okay, no problem. Harshi,
I don't know.
okay, no problem. So let's not try a third time. So let signal ET find as let it be a so does this qualify as a time limited signal? Aryan, this is defined for only or limited values of time. So is this a time limited signal? You two who I just asked the question. Okay, yeah, so I'll write this around myself. Time limited signal is one that defined only or given that or only within given
வெறும் ரசம் மட்டும் தானே இருக்கு மாட்டனே
no Baluke. Okay, so how do you pronounce your name? Balukesh? SVKNO Balukesh. So is the K silent?
Yes, sir.
I just want to know. Yeah, is the K silent in your name?
yes, sir.
Okay, so it's no Balukesh.
Yes, sir.
Nice. Anyway, only within a given time interval. Similarly, we can define a frequency limited signal as one whose Fourier transform is non-zero only within Z that is given frequency limited if fine and zero otherwise. This is how we define frequency limited signals. Now the question is, I'll try red. Can signal be both time and can anyone tell me the answer or can anyone guess the answer?
Yes, a signal can exist.
Okay, such a signal can exist. Okay, So unfortunately, the answer in this case is no. This is not true, or this is not possible. Reason, let us look at this. So any time limited signal GT can be expressed some HT time function.
Sir, if I take f is equal to 0, then
F equals uh, which F equals 0?
f of t, like it is both.
It's 0. It's totally 0.
So I think
Yeah,
it can be both.
yeah, that is the trivial solution. So we are talking about non-zero signals. You can by forcing a 0, you can do a lot of crazy things. But in general, okay, I modify my statement. Can a non-zero signal? That is a trivial case. Fine now, Navya. Navya,
Yes.
is this okay now? Okay,
Okay.
so the non-zero will come in a second. There's a lag. Hopefully, I'll be out of quarantine today. So Monday onwards, there will be no lag. Yeah, where this is the gate function such that fine. So this is the gate function, and so ht is any arbitrary function that equals gt in range of okay. Yes, fine. So now with this said, I know using the properties of Fourier transform, I know that g of f equals h of f convolved with the Fourier transform of right. Right. And this rect of rect t minus tau by delta is a scaled and time shifted right. Agreed. I hope you agree. And we know that the Fourier transform of pulse is, now tell me arbitrarily, Aryan, what is the Fourier transform of a gate pulse? Aryan, what is the Fourier transform of a gate pulse? Okay, cool. Navya, what is the Fourier transform of a gate pulse? Yeah.
Fourier
Navya, come on.
transform.
Yeah. Gate pulse, yes. The first thing that you derive, or the first thing that you see in practice questions.
Sync function.
In function, Pavan. Thank you, Pavan. So, is a sync function or a phase, in this case, a scaled and phase shifted, which means that I am convolving whatever is the, and sin function you know is sine right. So, an ugly representation can be this. Yeah. So, guys, there's a power outage. The Wi-Fi is gone. So this is via my mobile network. So the screen will be back as soon as my laptop gets back online. Okay, the screen is still showing the screen. That's a good thing. My laptop is just making sounds that it cannot find the internet. In another few seconds it will be back. So anyway, this is okay, right? So this means that, okay, the internet is back. Yeah, the internet is back. No, the internet isn't back. Still linking. Check it. I'll just use my phone. Okay. Yeah, so the lights are back on. You should be able to see the screen in another couple of minutes. Why is it? Oh, so there is an outage. Wait a second, let me, yeah, connect it. Okay. Check it. I'll just use my mobile hotspot. I'm just connecting via my mobile hotspot. Give me a second. So this, ask you. So you can see the screen yet, guys, or not? Guys, can you see the screen?
Sir, it's not visible.
Not visible. So maybe this is because my mobile. Oh, so the actual internet is back. So I'll unshare and yes. So unshare and reshare. So Now can you see the screen?
No, sir.
Not even now.
No, sir.
Okay. This is not good. Just a second. Hold on. Yeah, it's not visible. I see that on the phone. Okay. So let me continue with my point here. When the screen becomes visible, I'll start writing again. Is that okay? We don't have any other choice actually. Yes. Okay. Yeah. So what I was saying was that when you have a time limited signal, you basically end up having the Fourier or in the frequency domain. If you look at it, what ends up happening, yeah, what ends up happening in the frequency domain is that you have a signal, you have the Fourier transform of an arbitrary signal convolved with the Fourier transform of a rectangular function or a gate function, which in turn results in, or since we know that the gate function is unlimited in frequency or is covers all the possible frequencies. So yeah, guys, is the whiteboard visible now? I shared that.
No, sir.
Whiteboard is also not visible. Let me try that again. Okay. Now,
No.
oh, we just. So should I simply say that we are having a bad day? But yeah, not good. Wait a second. Am I using the wrong link there? Ah, hold on a second. Yes, Yes. I'm the only one in the new meeting on the laptop. That's why. Oh, there are two meetings running parallelly. Now there's just one. So now the screen should be visible. Teams, in all its wisdom, start another meeting. So, yes, now it's there. Now the screen is visible. So we have a scaled and phase shifted version of the sync function in the frequency domain that is being convolved with the Fourier transform of HD. Now we know that the sync function looks like this. Therefore, since the sync function looks like this, we know that this is not limited in frequency, and as a consequence, since convolution results in signal that are, or since the length of a convolved signal is longer than the length of the either of two signals being convolved, the signal being convolved with this can also be limited. Fine. And via duality of the Fourier transform, we can easily argue that via duality of the Fourier transform, what? We can easily argue that a signal that is limited in frequency can not be limited in time. So, however, a signal can be, well, for the want of a better word, unlimited. Both fine. So that said, if we have a signal that has a limited duration T1 to T2 can define its range. Similarly, there is something called the bandwidth so any guesses on what could be the bandwidth of a signal? Okay, since we are running short on time, the bandwidth of a frequency limited signal defined as the range of frequencies on 0. However, most practical signals are time limited, and by virtue of this property cannot have a precisely defined. Therefore, we define the following special one 3 dB bandwidth, the range of frequencies the amplitude, the signal or signal spectrum falls off to 1 by root 2 of its. So, how many of you understand this thing called dB, decibels? First of all, yeah. So, how many of you understand dB? Raise hands. Okay, you have you heard of decibels? When they measure noise pollution, have you ever heard of this term? Decibels.
Yes, sir.
Yeah. So, but from an electrical engineering perspective, have you encountered this term in any course till now?
Yes, sir. Like,
Where? Where?
like in the graphs, when we are calculating gain, 3 dB is equals to 20 log.
Okay, so how do you define dB? First of all, decibel. How do you define it? Okay. Sorry. So see, decibel, or dB, is a unit for relative power. So I'll talk in the terms of an amplifier. So I will talk in the terms of an amplifier. Consider an amplifier that takes sinusoid with an amplitude A1 and gives out A2. Then how do I define the gain of this amplifier? Yeah, how do I define the gain of this amplifier? Then no, gain, simply gain.
A2 by A1.
A2 by A1, right? But the amplifiers were originally designed for audio, and humans perceive sound in the log scale. Did you know this? That humans perceive sound in the log scale? Or if you actually we'll perceive something that, okay, it's twice as louder, we'll say when you make something, so the difference between, if you move from 100 to 200 and from 10 to 20, then the difference in human perception will be the same. Or in order to say that, hey, this is louder, so you can say that 20 is 10 units louder than 10. But when you are hearing something, you'll say that the difference between 10 and 20 is the same as the difference between 40 and 20. So we humans perceive these gains or these power levels in a log scale, and consequently we had to come up with a unit of gain that was in the log scale. So if the input power is P1 and the output power is P2, then gain, sorry, here the gain is A1, A2 square by A1 square. Yeah, so who answered that previously? this is should be a2 square by a1 square because these are the amplitudes. And power is square of amplitude. And gain is always measured in terms of power. Right? So then gain or gain in dB is log to the base, or sorry, gain in bells, named after Alexander Graham Bell. You have heard his name, right? Is log
Yes,
to the
sir.
base. Yeah. So this bell is named after Alexander Graham Bell, and this. Now this used to give pretty obscure values, or something point something, and that would be large. So what people figured out that hey, if we multiply it by 10, if this quantity we multiply it by 10, then that will be quite convenient to handle. So thus came the unit decibel, where 1 bell equals 10 dB decibels, and gain in decibels is simply 10 log to the base 10 P2 by P1. And since amplitude square, power is proportional to amplitude square, gain dB equals fine. Okay.
Yes, sir.
Yeah, great. Now 3 dB means that the amplitude is, or the power at the 3 dB point, power 3 dB point is 10 to the power, or rather I should, okay, so I have a room here. If maximum power is P0, then power at TTP point P1 or P3 is that 3 equals 10 log to the base 10. Right? Because P0 is the bigger one. Fine? Or P3 equals so this is also called the half power point, and the amplitude is max of the maximum. So, yeah. Then so do you guys have a class or something at 4 p.m. or should I continue? I'll finish off bandwidth and then stop. because we lost some 10 minutes due to the power outage. Guys,
Sir, I have an open elective.
okay, you can. So then let's stop here. And Monday, okay, you guys have an open electives all the time. So maybe I'll take some 20 minutes extra someday. Or what I'll do is I'll keep on piling these 20 minutes. I need 20 extra minutes for covering this up. So I'll keep piling these 20 minutes because internet disruptions happen, and we'll create an extra lecture out of those 20 minutes. Fine. So we'll have an extra lecture sometime. So this is the first part of the 20 minutes. Okay. Okay then. Bye all of you. Have a nice day.
Bye, sir. Have a nice day.